Good morning to all of you.
Good morning, sir.
So, is my screen visible?
Yes, sir.
Okay. So, are there any questions, doubts? Yes, any question, any doubt, anybody? Okay, so if there are no questions, so let me start. So, we are discussing viscoelasticity. So, let us continue. So last class, no, I couldn't do much, but what I had done was how to get the delta sigma xxan as a no, and in terms of delta sxxn comma I as a recursive relations, and similarly we did for delta tau xyn using the recursive relation. So that is what I had done. So from there, let me again come back to the constitutive relation and then the element level governing equation. So if you recall, we have already derived this expression for delta sigma xx is equal to uh, twice of delta epsilon xx minus one third of delta epsilon v volumetric strain, and this whole thing into g infinity plus this we have derived, so now you can refer to previous lectures. So this was gi tau I upon delta t into 1 minus to the power minus delta t upon tau I. So we have thus the final expression is plus k into delta epsilon v. This is a volumetric part, mean stress, and then we have this memory term delta sigma xxn, which is basically defined integral 0 to tn, and basically g at tn plus 1 comma t minus t dash into minus g at tn minus t dash into the that entire term in the definition what we have given. So this is what we have. So now I want to know finally put it in a somewhat simpler form. So let me say that delta sigma xx is equal to this whole term. This term is, let us say, call it as g dash. So then you can write it as twice of delta epsilon xx minus 1 upon 3 delta epsilon v into g dash plus k into delta epsilon v and plus delta sigma xxn. So this is what we have, and here this g dash is nothing but g infinity plus summation I going from 1 to n gi into tau I upon delta t into 1 minus e to the power minus delta t upon tau I. So this is your g dash, and delta v you already know that delta v is delta epsilon v is delta epsilon xx plus delta epsilon yy plus delta epsilon zz. So now what we can do is I want to write it in terms of delta epsilon xx, delta epsilon yy, and delta epsilon zz. So this delta sigma xx can be written as, so now this is g dash, and here you will have this k term coming, so k into delta epsilon v, which is delta epsilon xx plus delta epsilon. So if you collect the coefficient of delta epsilon xx, delta epsilon yy, and delta epsilon zz, so you can write this as 4g dash upon 3 plus k into delta epsilon xx. So you have one delta epsilon xx term here, one term here. These two are coming with g dash, and this is with k. So that is what you will have. And then the other terms are coming from no this delta epsilon yy and delta epsilon zz. So let me write it in this form. So you can write it as 2g dash upon 3 minus k, so into delta epsilon yy, and minus 2g dash upon 3 minus k into delta epsilon zz. So this is straightforward. Like delta epsilon v, you put delta epsilon xx plus delta epsilon yy plus delta epsilon zz, and then collect the coefficients of delta epsilon xx, delta epsilon yy, and delta epsilon zz. So you get this relationship. So this is, and plus of course the last term is your delta sigma xx n. This is a memory term because this is integration 0 to tn, so it is referred to as memory term. So similarly, you can write the expressions for delta sigma yy, so that would be 4g dash upon 3 plus k into delta epsilon yy minus 2g dash upon 3 minus k into delta epsilon xx minus 2g dash upon 3 minus k into delta epsilon zz plus k plus delta sigma yn. So this will be no, you will have for similarly I have derived for only one, but no, then similarly you can write for delta sigma yy and delta sigma zz. These are the incremental stresses we have already defined. Delta sigma zz is sigma zz at tn plus 1 minus sigma zz at tn, so that you already know as per the definition. So similarly delta sigma zz would be equal to 4g dash upon 3 plus k into delta epsilon zz minus 2g dash upon 3 minus k whole into delta epsilon xx minus 2g dash upon 3 minus k into delta epsilon yy, and plus delta sigma zz n. So this is what you have. So similarly for shear stress increments we have done. So we have derived this. So we know that delta tau xy is equal to delta gamma xy. This no, the second term. No, first what I am writing is the second term in the expression. If you remember, no, the second term we have derived. So this is g infinity, I going from 1 to n, and then we have gi tau I upon delta t into 1 minus e to the power minus delta t upon tau I, and plus we have delta gamma, no, delta tau, so delta tau xyn. Yeah, so this is no, you can rewrite this as delta tau xy is equal to, I can write this as no, g dash. So g dash we have already defined, it is the same term which is defined as g dash earlier. So g dash into delta gamma xy and plus delta tau xyn. So similarly you can have delta tau yz as g dash into delta gamma yz plus delta tau yzn, and you will have delta tau zx is equal to g dash into delta gamma zx plus delta tau zx n. So this is the no, all the components. So now you see we have the the relationship between the incremental stress and incremental strain for all components. We have delta sigma xx, delta sigma yy, delta sigma zz, delta tau xy, delta tau yz, and delta tau zx. So what we can do is we can write this. So I want to write this relationship in the matrix form. So let me write that in the matrix form. So you can write it as this side. No, all of this can be put together into a matrix form. So delta sigma xx, delta sigma yy, delta sigma zz, delta tau xy, delta tau yz, delta tau zx. So this can be written in terms of the, now we have already derived the relationship, so now you can write the same thing in the matrix form. So we will have here delta epsilon xx, delta epsilon yy, delta epsilon zz, delta gamma xy, delta gamma yz, and delta gamma zx. So here in between the terms, if you look at it, is 4g dash upon 3 plus k, and then we have minus 2g dash upon 3 minus k, minus 2g dash upon 3 minus k, and then these three zeros. So here we'll have minus 2g dash upon 3 minus k, then 4g dash upon 3 plus k, and minus 2g dash upon 3 minus k. Then we have, so yeah, you have to basically, if you see, it is the the same relationship which I have derived, minus 2g dash upon 3 minus k, minus 2g dash upon 3 minus k, and 4g dash upon 3 plus k. And then other terms are, we have 0 0 0, g dash 0 0, then 0 0 0 0, g dash 0, and 0 0 0 0 0 g dash. So yeah, here you have this g dash. So I think it is a straightforward no, same thing written in the matrix form. Plus, in this plus you have delta sigma xxn, delta sigma yyn, delta sigma zzn, delta tau xyn, delta tau yzn, delta tau zxn. So let us refer to this as delta sigma, and this is because it is the relationship, this matrix gives the relationship between incremental stress and incremental strain. So let me call it as a tangent constitutive matrix CT, and let us call this quantity as delta delta epsilon, and let us call this as delta sigma n. So with these notations, we can write this relationship as delta sigma is equal to Ct into delta epsilon. Ct is, I said what Ct is, and plus delta sigma n. So you can write this relationship like this. So this is what we have got, and we now know how to get this. So Ct is straightforward. As long as your delta t is constant throughout, Ct is going to be constant. It is not going to change from step to step. Of course, delta sigma n has to be calculated for each n. So we have through the recursive relation and the relationship between s and sigma, delta s and delta sigma, we can get this quantity. So now coming back to the element level governing equations, if you recall, we have derived the element label governing equation. So yeah, what we have derived is, we had the for a general 3D case we did, and of course you can, specific cases you can always do. So we had B transpose into delta sigma dV, and this was equal to minus integration over volume, and we had B transpose into sigma n. So keep in mind, this is delta sigma n, this is sigma n. So sigma at Tn, that is delta, that is what sigma n is. So this term is there, and then of course the body force and the surface forces. So we have H transpose into FBdV, and plus we have integration over surface H transpose into Tn ds. So yeah, we have got this relationship. And now if we make use of this here, no, in place of delta sigma, if we write this, and then delta epsilon, we have already said that it can be written as b into delta dE. So you can see that by making use of this relationship, what we have derived, the relationship between incremental stress and incremental strain. So finally, this can be written as integration over volume. We have B transpose, and then delta sigma is Ct into delta epsilon is B into delta D. So this can be written as B transpose into Ct into B, and this you integrate over the volume, so gives you the incremental stiffness matrix, and then we will have delta dE. And the other known quantities you take to the right hand side. So now from here we are getting one term delta sigma n, and other terms will remain as it is. So we will have minus integration over volume B transpose into delta sigma n. So this term is going to be there. Now this is coming from this relationship. I am taking this to the right hand side. So this is dV minus integration over volume. We already have this term. So B transpose into sigma n dV, and plus the other terms, integration over volume H transpose into FB dV, plus integration over surface H transpose into Tn ds. This ds is a surface integral. So now, so this is, I think we have done. Now I have shown you all the steps in the viscoelastic finite element analysis of a viscoelastic, linear viscoelastic material. Of course you can extend it to orthotropic materials and so on, no, in a similar logic. No, the only thing is, then you will have the elements of the constitutive matrix directly expressed in terms of Prony series, and you can get the similar equations. So now let me explain you overall algorithm how you will do this viscoelastic analysis. So the whole algorithm is, because the problem is a time dependent problem, so we need to take time. So this is t equal to 0, then you have delta t, 2 delta t, 3 delta t, and this is n equal to 0, n is equal to 1, n equal to 2, 3, and now you will have somewhere this n minus 1 into delta t. So the n is n minus 1, then you will have n delta t, so this is n, and then you will have n plus 1 delta t, and this is n is n plus 1, and then so on. So this is the discretization in time. So let us see how the calculations would proceed. So first, no, we will at n equal to 0, because that's the starting point. So at for n equal to 0, we will know some of the, and also the initial stresses is say a null vector. No, the initial stress, initial strain at t equal to 0 is a null vector. Then the memory stress is also a null vector. Delta sigma at n equal to 0 is a null vector, and the displacement vector also at t equal to 0. So at 0 is equal to a null vector. So these are all given initially at t equal to 0. We know all the quantities are actually zeros and null vectors. So now the next calculation we will do for n is equal to 1. Hello, am I audible?
Sir.
Yes, sir.
Okay. Yeah, you can know, if you have any doubts and questions, you can stop me and ask. So now let us look at the calculate sequentially. So I will write all the steps. What are the steps involved in the overall analysis? So let us see that the calculations at n is equal to 1. So n equal to 1 means t1 would be equal to delta t. So no, you already know how to form the the we already know how to get B matrix. We know in terms of derivatives as a shape function. this tangent constitutive matrix is known, B is known, so you can calculate the element level stiffness matrix. And right hand side also you can calculate with all the quantities given. So because here when we are writing the equations for n plus 1th step, we will be, all these values are for the previous step. So for when we are doing the calculations at n equal to 1, so these terms would be evaluated at n equal to 0. So these two terms will be 0, and of course these are the body force and traction forces which are at n plus 1. So these forces are applied forces, they are at n, n equal to 1, the current time step. So now based on this you can get the element level governing equation, and then assemble, impose the boundary condition. So finally we'll get this kt into delta dE is equal to right hand side, the net right hand side I am calling it as f. So from this equation you will be no, not delta d, it would be delta d for the assembled system. And then from this you get you will solve this equation for delta d. And once you solve for delta d, then again you go to each element, and for each element you will get the no vector of element increment in the vector of elemental degrees of freedom. So now these are the kind of post processing calculations. So after you solve this equation you need to do some post processing of the data. So once you extract delta d, then you will get your delta epsilon, you can calculate, which would be at a particular gas point. This you have to do for each element at every gas point. So you will have into delta dE. So from this you will get delta epsilon. Then you want to calculate delta sigma. So delta sigma is going to be this ct into delta epsilon, we have already derived this, and plus delta sigma 0, because now this delta sigma we are calculating at basically n equal to 1, so delta sigma 0 will come. And delta sigma 0 is 0, so obviously delta sigma is simply going to be this quantity. Then you calculate sigma 1, that stress at the current time step. So this will be sigma 0, the stress at previous time step, plus delta sigma. After calculating delta sigma you can calculate this. Now we'll have to calculate the memory term, so we also need to calculate delta sigma 1. So let us see how to calculate this. So for this, as I said, we have derived those recursive relations, so we'll have to use that. So when we are using the recursive relation, so for each component of stress, sigma xx, sigma y, sigma zz, tau xy, yz, and zx, you have to do this calculation. I'm just writing for sigma xx and tau xy. So now for I, I is the number of I equal to 1 to n, so where n is the number of terms in the Prony series. So for this we will calculate for each of the I value, we will calculate delta sigma xx 1 comma I, that n is 1, so 1 comma I, this n comma I. So this is equal to, we have already derived this relationship, minus delta t upon tau I into delta s xx 0 comma I. This recursive relation we have derived, and this delta sx 0 comma I will be actually 0 at the initial time step. Plus we have 2 gi tau I upon delta t, and now we have already calculated the incremental strain, so you can get delta epsilon xx minus 1/3 of delta epsilon v, and this into we have 1 minus e to the power minus delta t upon tau I. So from this calculation of sx sxx 1 comma I, you have to do for all the values of I depending on how many terms you have in the Prony series. And also you have to do similarly for delta s yy 1 comma I. So you can write the similar relationship, and delta s zz 1 comma I. No, I'm not writing that, it's a straightforward. Delta s yy 1 comma I would be to the power minus delta t upon tau I, delta s yy 0 comma I plus 2 gi tau I upon delta t, delta epsilon yy minus 1/3 of delta epsilon b into 1 minus c to the power minus delta t upon tau I. So like that you can write. So similarly for I equal to 1 to n, you do for the shear components also similarly. So like you will have delta sxy 1 comma I will be e to the power, I am making use of the relations which we have already derived, e to the power minus delta t upon tau I into delta sxy 0 comma I and plus gi tau I upon delta t into delta gamma xy into 1 minus to the power minus delta t upon tau I. So you calculate this, and then now you know the relationship how to calculate delta sigma. So you will do this similarly, the calculation for delta yz 1 comma I you will calculate for each I, and delta s zx 1 comma I you will do the similar calculations for each I. And then now you can, then next would be the calculation of delta sigma 1. So delta sigma 1 would be then summation over all i's. So I equal to 1 to n, and then we have derived no delta sigma and s, the relationship is e to the power minus delta t upon tau I minus 1 into, now the s is already calculated, so delta s 1 comma 1 comma I. So from this you will calculate delta sigma 1. Now this delta sigma 1 would be used in the next step in the calculation of your right hand side, that is the load vector in the element level governing equation. So now let me also show you the calculations for the n equal to 2 and then finally n equal to n plus 1. So calculations at n is equal to 2, so that means it is t2 equal to 2 delta t. So the steps are same. Now for this your as long as your delta t is same, so you will find that your stiffness matrix kt is going to be same, that is not going to change. So you can store that, and the inverse of that you can store, and you can use it repetitively. But right hand side you have to calculate at every time instant. So now for n equal to 2, now in this equation you will see we will use here delta sigma 1. Now delta sigma 1 is non-zero, so it will contribute to the load vector sigma n, that is sigma, now 1 will be there which is non-zero, it would be used in the calculation of right hand side, and these are of course the loads at n equal to 2, fb and tn. So from that you get the load vector. So now in similar way, now you will, as I said, kt would remain same, and but the right hand side you have to calculate. So I'm again now using a, in an algorithm I'm using same notation f, and by solving this you will get your delta d, and then for each element you can extract your delta de, and once you get your delta de, then you can calculate at a particular gas point, you can calculate the incremental strain vector, because b has to be evaluated at a gas point. So this will, these calculations have to be done at every gas point. So you have to store of course all the relevant quantities at every gas point. So delta de, so this, from this you will get delta epsilon, and then you calculate delta sigma, the incremental stress. So incremental stress would be ct into delta epsilon and plus delta sigma 1, that is already calculated in the previous step. So then now based on this you will calculate sigma 2, the stress for the current time step. So sigma 2 would be equal to sigma 1 already available from the previous time step plus delta sigma, and then you have to calculate your delta sigma 2. So again you do the same same set of calculations which I have shown already. So that is for I equal to 1 to n, you will calculate delta s xx, now 2 comma I, because n is now 2. So 2 comma I is equal to e to the power minus delta t upon tau I delta s xx 1 comma I. Now this will also be non-zero, calculated in the previous time step, and then there is an additional term twice of gi tau I upon delta t into delta epsilon xx. Now for the current step for n equal to 2, delta epsilon is calculated, so you will get the components minus 1 upon 3 into delta epsilon v into 1 minus e to the power minus delta t upon tau y. So you calculate, no, same way you do for the delta s y and delta s z, you do the similar calculation. And then for the CR, so I'm just writing the one component of each. For I equal to 1 to n, you similarly do the calculation delta sxy 2 comma I equal to e to the power minus delta t upon tau I, e to the power minus delta t upon tau I into delta s xy 2 comma, now we will have, no, sorry, 1 comma I, 1 comma I plus we will have gi tau I upon delta t into delta gamma xy. This you would have calculated into 1 e to the power minus delta t upon tau 1. So you can calculate it like this, and then now you do the calculation. So you will get delta sigma 2. That will be, that's the final calculation for the step number 2. So this will be calculated as summation I going from 1 to n. Now the s terms are already calculated, so e minus delta t upon tau I minus 1 into this delta s, all the components of delta s. So that is delta s 2 comma I. So you calculate this, and this delta sigma 2 would be used in the next step. So now, like that, now when you want to generalize this, so the calculations at, now we, let's say we have done the calculations till n equal to n, that is t equal to n delta t, and then we want to do the calculation for the next step. So then calculations at n plus 1th time step. So again same thing, no, your kt is going to remain same, the stiffness matrix after assembly and imposition of boundary condition. As long as your delta t is same, this is going to be same, kt into delta d. Of course the delta d is going to change from step to step. I'm using the same notation of, although over here, no, this is equal to f. Now this is, see, kt is going to remain same, f is going to change. So when f is changing, delta d will change, so that you have to keep in mind. So from this you will solve for delta d, and once you solve for delta t for an element, and you have to do that for each element, so extract the element level, no, incremental degrees of freedom vector, and then you calculate epsilon at a Gauss point in the element, so which would be b into delta de. You calculate this, and then you calculate incremental stress in the current, no, this time step, which would be ct into delta epsilon plus delta sigma n. Delta sigma n would be available for the previous time step, and then you calculate, no, your sigma n plus 1, and this will be equal to sigma n plus delta sigma. So there are two sigma delta sigmas. One is delta sigma, just delta sigma, another is delta sigma n. So you should note the difference between the two. And then you calculate, say for I equal to 1 to n, the same set of calculations for the memory terms. So that is delta s xx n plus 1 comma I will be equal to e to the power minus delta t upon tau I into delta s xx n comma I. So this relationship be the same what we set for the step 1 and step 2. So 2 gi tau I upon delta t into delta epsilon xx minus 1/3 of delta epsilon v into 1 minus e to the power minus delta t upon tau I. So you do this calculation, same thing you do for delta s yy, delta s zz, and similarly for I equal to 1 to n, you do delta s xy n plus 1 comma I is equal to e to the power minus delta t upon tau I into delta s xy n comma I, and plus we have gi tau I upon delta t into delta gamma xy. Keep in mind, no, that every step the incremental is, no, the strains are going to change. So delta gamma xy into e to the power 1 minus delta t upon tau I. So you calculate this, and then now you get the delta sigma n. So delta sigma n will be calculated from this, will be I equal to 1 to n e to the power minus delta t upon tau I minus 1 into delta s n plus 1 comma I. So like this you do the calculations. So this is how the entire set of calculations will go.
Hello.
And yeah,
Delta sigma n plus 1.
pardon.
It is delta sigma n
Delta
plus
sigma
1
n plus
last
1.
term.
I think two of you are speaking simultaneously, so I'm not able to hear you correctly. Please repeat again.
For the left hand side of the last equation is delta sigma n plus 1.
Yeah, yeah, yes, yeah. Thanks for the correction. Yes, it is delta sigma n plus one. Yeah, thank you for this correction. Anything else? So yeah, so this is actually no, this is what I wanted to discuss in linear viscoelasticity. So we have I know, of course, you can, in specific cases you can always do as a, now this for the 3D what we have discussed. Now you can reduce it to 2D plane stress plane strain problem or axisymmetric problem, or you can do the similar thing for 1D. So I know, as a no, I'm not going to ask this what I'm just going to give you, but as a homework problem. So the homework problem you try for, let us say we have a uniaxial no problem where we have, let us say, sigma xx, just only the one component of stress is non-zero. So sigma xx at t is equal to integration 0 to t e t minus t dash into d epsilon xx upon dt dash into dt dash. If you have this relationship, this is just the uniaxial case, and know the E is given as a promissory. So E as a function of t would be E infinity plus summation I going from 1 to n e I e to the power minus t upon tau I. So if this is given, you develop all the equations. So now you're just going to work in terms of this relationship itself. You're not going to decompose this into debatoric part or anything like that, but you directly work with this relationship. So only one non-zero component of stress, that is sigma xx, and you have the Prony series in terms of the Young's modulus. So this term is there. Now develop all the equations. Develop all the equations discussed so far for viscoelasticity. So this is a homework problem. No, you should try doing the incremental form, knowing the relationship between delta sigma xx and delta epsilon xx, and then the element level governing equation, the recursive relation for getting delta sigma xx n plus 1 and delta sigma xx n. So that recursive relation and all you try to develop for this. So yeah, this is now what I want to do is next. Yeah, so now the I think I want to discuss dynamics first, and then I will go for the finite deformation problems, the geometric nonlinearity problems, and then the contact nonlinearity. So now let me go to dynamics. so far whatever we have discussed is the statics problems, either the quasi-static like viscoelasticity or no statics problem. That is what we have done. Now when we want to go into the dynamics, so in dynamics we know basically your externally applied forces, externally applied forces are functions of time. And not only this, if it just the externally applied forces are functions of time, but if the inertia forces are not important, then you can significant, then you can actually still do a quasi-static analysis without including the inertia time. But when we are saying dynamics, so the forces are functions of time. More important is that the inertia forces are significant. Inertia forces are significant. So this is what we need to include the inertia forces in the the governing equations. So far whatever we have developed the element level governing equations. So first I will take a simple example. I think maybe some those of you might have done basic course in FEM, you might have, some of you might have done it, so it is going to be kind of repetition. So now how do we do this? So first let me discuss the energy based approach. Of course we can always start from a differential equation, write the better terrestrial statement weak form, and then develop the element level governing equation including the inertia forces from there. But let me first discuss with the energy approach. So in energy approach, additional thing we have so far talked about the potential energy of conservative forces, and know the basically the internal as well as external forces. So now additional thing which will come in dynamics is the kinetic energy. So now if you look at the kinetic energy, so general case, how do we define kinetic energy? So this is notation I'm using is T for the kinetic energy, half, then the integration over volume rho you have, and then general case let us say the velocities are u dot, v dot and w dot. So u dot is square plus v dot is square plus w dot is square into dv. So this is how you calculate the kinetic energy, and we are going to for different elements no we can specialize this relationship and write for that. So the simplest case, let us take a two noded truss element and develop the expression for kinetic energy and then subsequently the mass matrix for the element. So two noded truss element. Two noded truss element means only non-zero component of stress is sigma xx, and then non-zero displacement is u. So this is the element. This is node 1. This is node 2. The local coordinate system is capital X, and this is displacement. Now for the dynamics problem, these are going to be functions of time. So displacement at this point u2 is also a function of time t. So for this two noded element, if you know the u, you know the displacement at any point over here, if you take any point, so u which is a function of x and t will be in terms of shape functions, those remain same. So you will have n1 n2 and into u1 which is a function of time, and u2 which is a function of time. u1 and u2 are the values of u at node 1 and node 2. So this is what you have. So now if you want to calculate the velocity, so velocity let me denote it by u dot. So u dot will be n1 n2, because n1 n2 are only functions of x, and u1 dot and u1 and u2 are the functions of time. So we will have u1 dot and u2 dot. Dot is the time derivative, where the these terms n1 is equal to 1 minus x by l we have already derived earlier, and n2 is x by l. So you know these quantities. So yeah, this I am directly writing over here this expression for u as a function of x and time, then velocity u dot, and this is the only non-zero velocity. So now if you look at the kinetic energy T, so T is half, and integration over volume can be expressed split into integration along the length, so 0 to L, and the integration over the cross sectional area. And then you have rho, and the only non-zero component of velocity is basically u. So in the general expression, now this expression you will have only non-zero, u dot is non-zero, v dot and w dot are zero. So we will have u dot square into dA dx. So this is for d capital X, because that's the local coordinate. So d capital X. So this is going to be the kinetic energy. Now if you see, u is only what we are taking, this u dot is only function of x. So the integration over the cross sectional area will simply get the cross sectional area at a given x. So we can write this integration as 0 to L, and then rho into a into u dot square into dx. So this is what is your kinetic energy. Now because we have u approximation of u dot in terms of this shape function, so we can write no t, we want to write in the matrix form properly. So integration 0 to L, we have rho a, and this you can write as u transpose, u dot transpose into u dot into dx. And yeah, this relationship you can write as the interpolation matrix n into de dot. So this is, let us say, is n into de dot. So this I am saying as h, and this one I am saying as de dot, vector de dot. So now if you substitute these, so if you look at the kinetic energy, can be written as half integration 0 to L rho a, and then u dot transpose would be de dot. This is the nodal velocity vector for the element. So d dot transpose into h transpose, and then you will have h into de dot dx. So this will be the expression for the kinetic energy. Now since d dot is the the elemental nodal velocity vector, and it is independent of x, so that can be taken out of the integration sign. So you can write that as half, and then de dot transpose integration 0 to L rho a into h transpose into h into dx. And then you finally have this d dot this side. So you can write it like this. Now we write here, this is t, this is t. So we can write t equal to half of de dot d dot transpose, and this is, I am denoting it as elemental mass matrix. So let us say that is me, and into de dot. So this is the finally the kinetic energy in terms of mass matrix me. So where your me is equal to integration 0 to L rho a h transpose into h dx. So this is your me, and we call it as element label or elemental mass matrix. So this is what you get as the the mass matrix for this two noded truss element as integral 0 to L rho a h transpose h dx. So now if you look at the, if rho a is constant within the element, if rho a is constant within the element, then we can write now this me as rho a you can take out of the integration, then integration 0 to L, you will have h transpose into h dx, and now you can say that if you put your h, so that is rho a integration 0 to L, H transpose is going to be H is n1 n2 basically a row matrix, so its transpose will be a column, so we will have n1 n2, and then H is of course this n1 n2 dx. So if you do the calculations, you can write this as integration 0 to L, multiply these two, so we'll get n1 square n1 n2 n2 n1 and n2 square dx. So you can, if you do the integration now, n1 n2, n1 is 1 minus x by L, and n2 is x by L, so you know that. So the mass matrix ME will be, you if you do those integrations, so you will find that this will come out as L by 3. Integral n1 square will be L by 3, n1 n2 would be L by 6, n1 n2 L by 6, and L by 3. So this is what no your uh, this mass matrix is going to be. So if you take row AL upon 6 as common, so we will have here 2 1 1 2. This is the element level mass matrix for the truss element. So similarly, now you can derive the mass matrix for different elements. So I will talk about that in the subsequent lectures for different elements, how to get the mass matrix. And since this mass matrix we have derived from the whatever interpolation we have used, so this is known as current mass matrix, because this is consistent with the approximation of the displacement within the element. So this is known as consistent mass matrix. Of course, now that the another property of this mass matrix you can notice, that if we sum all the elements, so 2 plus 2 4 plus 1 plus 1 6, so rho L by 6 into 6, it will give you rho L. So because this element involves only translational degrees of freedom, that is u1 and u2, so sum of all the elements of the mass matrix is equal to total mass of the element, that is rho Al is the total mass of the element. So that is the property you actually use. Sometimes you also use what is known as lumped mass matrix. So rather than calculating the mass matrix from the consistent derivation based on shape functions, you approximate the take the total mass and distribute at the nodes, a lump at the nodes, so that is known as the lumped mass matrix. So in this case, now the simple way could be lumped mass matrix could be ME is equal to total mass distributed between the two nodes. So you have rho L by 2 divided by 2, and then 1 0 diagonal elements, you have only diagonal elements are unity, off diagonal elements are 0. So this is known as lumped mass matrix. So this is a consistent mass matrix, and this is a lumped mass matrix. We have taken the, in the lumped mass matrix we have taken the total mass divided, and there are two nodes, so total two nodes, we have equally distributed the mass at those two nodes. So rho L by 2, rho Al by 2 at the two nodes. So this is also sometimes we use the lumped mass matrix. Of course, now from the calculation point of view, when you are interested, usually if you use the lumped mass matrix, you get more accurate eigenvalues, and if you use consistent mass matrix, you get more accurate eigenvectors. So with lesser number of elements, you can get more accurate eigenvectors or eigenvalues depending on which mass matrix you are using. Consistent mass matrix or a lumped mass matrix. Yeah, so then once we have mass matrix, so then see we need to develop the element level governing equations. So how do we develop the element level governing equations? So if you are using energy based approach, so then you use what is known as the no, Hamilton's principle. So to derive the element level equations of motion or equation of motion. So the energy based approach means we use Hamilton's principle. So Hamilton's principle statement is that integration between two arbitrary time instances t1 and t2, then we take delta t minus delta v plus delta w and c dt equal to 0. So this is the statement of Hamilton's principle where delta T is kinetic energy, V is potential energy, and delta W and C is the virtual work of non-conservative forces. So delta T is first variation of kinetic energy T, and delta V is the first variation of potential energy V of conservative internal and external forces, of conservative forces. These can be internal as well as external. I mean, it includes internal means due to stresses. And delta WNC is the virtual work of non-conservative forces due to kinematically admissible virtual displacement. It is important that no the whatever virtual displacement we take, it should be kinematically admissible. That means it should satisfy the homogeneous form of the essential boundary condition. Force due to kinematically admissible virtual displacement. So now this is the Hamilton's principle. We want to use this to develop the element level governing equations. So how do we do this? So we need to write the expression for delta T, delta V, delta W and C. So if you look at T, we have already written as half of D transpose. So we know that T, we have already said, can be written in the form of half of D dot transpose into element level mass matrix ME into DE dot. So if you do delta now from this, if you want to take the first variation of kinetic energy, so delta T will be half, and the variation is with respect to unknown quantity. So the mass matrix is known, dot is the one which is unknown. So we will have delta of DE dot transpose into ME into DE dot, plus we will have half of DE dot transpose into ME into delta of DE dot. So this is how you can write it. And now in this, because both are scalar quantities, so like if you look at mass matrix is a 2 by 2, and this vector is 2 by 1, and this transpose is 1 by 2, so finally it's scalar. This is also 1 by 2, 2 by 2, and this is 2 by 1, so finally the product is a scalar. So now if this is a scalar, so this term can be replaced by the second term we can replace by its transpose. So if we take the transpose, then it would become exactly similar to the first term. So that means we can write this term actually as delta of D dot transpose into ME into DE dot. So you can write it like this. So that is delta T. First variation in the kinetic energy can be written as delta of D dot transpose into ME into DE dot. So that half goes because these are the two terms. So half into 2 gets cancelled. And on this I said we can write it as its transpose. When we write it transpose and open that, we will get exactly the second term similar to the first term. So we combine them and we get this. Now if you look at the now in this case the potential energy, so let us only include the strain energy part in that. So now V, I am going to use only the strain energy. So delta V, I am going to write similarly, you can write it as delta D transpose into Ke, the element level stiffness matrix, into DE. And then the virtual work of non-conservative forces, including, let us include all the internal and external forces. So we will have delta DE transpose into F external for the element, and plus you have delta dE transpose into F internal for the element. So both these forces, external and internal forces, are, because they are functions of time, so they would be non-conservative. So I am including them in the virtual work of non-conservative forces. So this is delta T which is needed in the Hamilton's principle. This is delta V which is needed in the Hamilton's principle, and this is the virtual work of non-conservative forces which is needed in the Hamilton's principle. So if you now we want to substitute this in the uh, now we want to substitute this in the Hamilton's principle. So what do we get? So now again going back to Hamilton's principle, you will have the integration from T1 to T2, and then the first term is delta T, so which is delta of dE dot transpose into ME into dE dot. This is the first term. Then minus we have delta V. So delta V is delta dE transpose into Ke, the element label stiffness matrix, into dE. So and then we have, so this is delta T, this is delta V minus delta V plus delta WNC, and delta WNC is delta dE transpose, and then let us sum these two, F external plus F internal for the element, and this is equal to 0. Now we want to invoke the arbitrariness of delta D, because now the virtual displacement delta D or variation in D is arbitrary, and no, delta D of course is in this case an dynamics problem. D is a function of time, delta D is also a function of time. So as far as this term is concerned, in the we want to bring in delta D, the first term, which is coming from the first variation of kinetic energy. We want to bring in basically the delta D. So how can we do that? Is through the integration by parts. So we do the integration by parts. We use integration by parts for the delta T term. So from that, now we will get integrate no the when you do the integration by parts, so we will have, and in that we want to uh, take the this function as the first function. So you will get basically delta delta D, so we'll get delta D transpose into ME into dE dot, that remains as it is, minus integration from T1 to T2, the integration of the first term, so that is delta D transpose into ME, and the derivative of the second. So when we do the derivative of the second, we will get dE double dot. Now the second term is basically this one and its derivative, so we will get here dE double dot into dt, and the other terms remain same. So plus the uh, this term remains same. So yeah, the other terms are basically minus integration from T1 to T2 delta dE transpose into Ke dE dt, and plus you will have integration from T1 to T2 delta dE transpose and F external for the element plus F internal for the element, and this whole thing is equal to 0. Now in the first term, if you look at, this is evaluated at T1 and T2. So this is at T1 and T2, and we said now we have to choose T1 and T2 such a way that delta D is 0 at these two time instances. So delta D at T1 is 0, and delta d is at t2 is 0, so this whole term will go to actually 0. So then what you can write is, now if you look at this integral, you can write it as, no, let me take the minus sign out, so I can write minus and then integration t1 to t2 delta dE transpose, and inside I will have, no, this term is 0 and this is me into dE double dot, that's the first term, minus we will have ke into dE, that's the second term, and no, mine not minus, plus, because we have taken a minus sign already outside. So this term is minus, this term is minus, so they will be plus inside. And minus, you will of course have delta D transpose is taken as a common, so you will have F external for the element minus F internal for the element, and this whole thing integral dt is equal to 0. So this is what we get when we substitute